All right, problem number one. So we're going to jump into the second practice exam. We're going to solve it like we've never solved before. So here we go. First, we notice using the guides that we've talked about before, we've got no speed, we have no height, and we have this compressed spring, and that tells us that all of our energy when we start off is elastic energy. And then what ends up happening is that we have both kinetic and gravitational because we have h greater than 0 and v greater than 0 at the top of the loop. So that tells us that we have kinetic and gravity. Also, we're told assume for parts A and C no dissipated energy. So that means we got some kinetic, some gravity. Our spring has sprung, so there's no elastic and there's no dissipated energy at all. So when we write down the energy conservation equation, we would write that E elastic equals EK, the kinetic energy, plus the gravitational energy. We're simply setting this bar graph equal to that set of bar graphs there. So if we want to determine the spring constant of the spring, what we're going to do is we actually use the formulas from this page here. So we're going to use all of these formulas for problems 1 and 2. And let's just jump in and use those letters. So it's going to be up to you to kind of look over this carefully on your own time. But for the purpose of this video, we've got 1/2 kx squared equals 1/2 mv squared plus mgh. And let's actually put in the numbers that we have. So, we have an unknown k. We were told the compression of the spring was 0.5 meters. So we'll square that. Plus 1/2 times m times v squared. So we've got a 2 kilogram car going 5 meters per second. And we'll square that. Plus 2 times 10, which is g. And the height of our loop is also 2 meters. So that's how we'll set that up. And so what this is going to give us when we simplify a little bit further, I'm going to actually have to do it down here. We're going to end up getting that 1/8 k equals 25 plus 2 times 2 is 4 times 10 is 40. So the k that we get is actually going to end up being 65 times 8, which is going to be about 520 Newton meters. All right. Now, let's go ahead and calculate, sorry, that's newtons per meter. Now we want to repeat the experiment and figure out what the energy dissipated is if we only have 4 meters per second at the top. So very similar formula. But now for part D, I'm going to actually make this note here. And I'll write it in blue. I'll say plus E dissipated. And I'm going to write 4D here. And so we'll end up getting similar 1/2 times 520 times 0.5 squared equals 1/2 times 2 times 4 squared plus 2 times 10 times 2 plus E dissipated. And when we actually simplify and get E dissipated, I'll just tell you right now, I ended up getting E dissipated is 9 joules of energy. Now, the hint that I gave in class, when you read the word force in an energy problem, that's an indication that you need to use the work formula. So we're told we've got 9 joules of dissipated energy, and that is caused by the friction force acting over this 3 meter distance. And so finally, we're going to end up getting a friction force of 3 newtons. So that's it for problem number 1, and we will tackle the other problems in future videos.